But here we're asked to write the correct formula from the name for a number of compounds. These ionic molecules have elements from the periodic table that can have more than one oxidation state, meaning they can lose or gain more electrons than just a fixed number. And that number is always going to be indicated in a Roman numeral in parentheses. So here we have iron and oxide. So if you look up iron in the periodic table, the symbol is Fe. That should be straightforward. Oxide is the ion that comes from oxygen, so it's an O. Now, in the case of oxygen for ionic compounds, we don't have to worry too much about the oxidation state because it's typically -2. It tends to gain 2 electrons, so you're going to put -2 there. Now, the iron is the problem, and we are told by the name of that formula that there's a Roman numeral 3, which indicates the oxidation state of iron, meaning it has a charge of 3+. So I'm going to put that +3 on top of it. And all it remains is to use our trick of crisscrossing. We bring the 2 without the sign in front of the iron. We bring the 3 in front of the oxygen. I can erase my reference charges. And that should be the formula for iron 3 oxide. Now, how to enter it? Well, we need to use the subscript tool here on the template. Get out of that template, capital O for oxygen, template again, the 3, and that should be what we submit. Always read the explanation if there's one, because it has some good information that will reinforce what you are learning. So I'm going to skip through some of these because, well, let's do manganese 4 oxide just because of that 4 being quite unique. Manganese have multiple oxidation states. If you look it up in the periodic table, it has the symbol Mn. It's different than magnesium, so this is Mn. And it's another oxide, so we're still going to use the capital O for oxygen. Now, the formula tells you that you have an oxidation state of 4, so it's going to be 4+, 2- for the oxygen. This one requires a little bit of thinking because the numbers that we're going to get by crisscrossing are the following: a 2 here and a 4 here. I'm going to erase my guide. But before I commit that answer to the homework, whenever you have numbers that can be reduced by dividing them by a common denominator, you need to do that. So for instance, 2 and 4 are multiples of each other, right? 4 is twice as much as 2. So if I divide both numbers by 2, I get a slightly different formula. I get Mn1 O2. Remember, the 1 is not written, it's implied. So I'm going to get rid of it. But that formula and that formula, when you record them, they're different. They indicate the same ratio of manganese to oxygen. So there's nothing wrong with that. But it's not the simplest form of the formula. So we need to go with the simplest one. That's the way chemistry works. We try to simplify things, as ironic as it may seem. So I'm going to enter this one first just to see what happens with the system, and then I'll enter the correct one. So we have Mn. I'm going to go with the non-reduced formula, the one with the original subscripts indicated by the charges, and see what it tells me. So incorrect, flat out, but what is it saying? use the lowest whole number ratio. So right there is the common denominator thing that I mentioned before. We need to reduce these to the lowest whole number ratio for each ion to get a balanced charge, a charge of 0. I'm not worried about the charges because I use my guide on the top. I had a +4 and a -2 there. So the charges should cancel out okay. But these numbers are not the simplest whole number numbers that we can use. Those are. So let's enter it again with those changes. I don't know if he's going to, oops. Let me enter that. And that one it did like. Any questions about that type of questions? All right, so let's move on to the next one. Now here we are with polyatomic ions. You need to pay attention to the name because some names are very similar to each other. And then when you look at the formulas, they are also very similar to each other. So for instance, phosphorus has multiple polyatomic ions that it can form. But noteworthy are this top one and this bottom one. So phosphate, phosphite. Slight difference, completely different chemical, completely different properties. They behave differently. They are chemically very different. PO4, 3 minus, PO3, still 3 minus. So pay attention to every detail, name, symbol, charge, everything has to be carefully considered. Sulfite and sulfate are another example. With chlorine, you have perchlorate and chlorate. So there's a prefix there. Chloride and hypochlorite. So 4 different polyatomic ions for chlorine, each one with a different number of oxygens, all of them -1. All of that we need to take into consideration. So in this exercise, we're going to use that table to simply select the correct name of the chemical indicated. So what does it say? Sorry. I didn't even read the question carefully enough. It says, select the correct name up here for K3PO4. So let's put that formula here, K3PO4. Now, before we go to the metal, let's go to the polyatomic ion. So PO4 on this table was at the bottom, and I believe it was called phosphate. It's actually bolded. So this is the only PO4 on all of this table. There's no other PO4. So it's going to be phosphate. Now we're not having to check the formula, but we'll do that in a minute. So we have phosphate for the second part of the name. The first one is easy because those don't change. They just take the name from the periodic table, whatever appears to be K. The 3, don't worry about the 3. It comes from the fact that this has a charge of 3 minus and this is +1. So crisscrossing, that's what you get. So it's simply potassium. Make sure you spell it right because sometimes I spell it with 2 T's instead of 2 S's. And is there potassium phosphate in this list? It's the top one, right? It's not this one. That's potassium phosphite. So be careful. We're going to pick the top one. And you may have a different question on your homework, but that's the way we answer it. Questions about that one? Okay, so let's move on to number 16. Same thing. This time is potassium phosphite. So I'll let you answer that. Oh, this is reverse. So this is the formula instead of picking the name. Let's do this one then, because there's a difference there. So we have potassium phosphite. We're going to keep the potassium there. That doesn't change. We're going to copy the name, the symbol for the polyatomic ion phosphite. And that's PO3 with a charge of 3 minus. So instead of PO4, it's PO3. But the charge remains the same. So guess what? The formula is going to be the same, except that instead of PO4, it's PO3. But it's still a 3 here. That 3 comes from these 3, crisscrossing. This one is not written because it's implied, but it's there. It's invisible. And that's what we're going to choose for the formula, K3PO3. So it's the third one in my example. In fact, some of these other formulas are wrong. They don't exist. KPO4 doesn't exist. Sorry, KPO3 doesn't exist. KPO4 doesn't exist. This one is the one that we named before. Okay? Okay. So that's similar but in reverse. So write the formula including the charge for each of the following polyatomic ions. Express your answer as an ion. Hydrogen carbonate. Well, we need that table that we had before we can even begin to answer any of these questions. I don't memorize them all. So let's look at bicarbonate, hydrogen carbonate. Okay, so HCO3 is what we need to remember. HCO3, let me remember the charge too, just to see how we have to enter it. And the charge is -1? Or, yes, -1. Let's go back to the problem then. Express the answer as an ion. Okay, so let's see if we can enter it there. HCO, now we need the template for subscript. Oops. 3. Now, is there any other indication as to how we're going to put the charge?
They want you to put the charge, negative or positive.
And does it have to be like a superscript? It doesn't say.
I think click after it and then put the negative.
Okay, so let's put -1.
Oh, wait.
No.
You're supposed to put the XA and then put one negative.
So then they do want the superscript.
Yeah.
Okay.
That's
Let me try it like this first, just out of curiosity.
yeah.
That's not quite right. Please check your formatting and try again. Okay, so
I came.
Juan is right. Oops.
Yeah, you're right. It's
The superscript
Yes.
template. Okay. Now, as before, does it matter if we put the negative sign first? Does it want the 1? Sometimes it doesn't want the 1.
first and then the negative sign. But
Okay,
the 1
so-
just put the negative because there's no, you don't put the 1.
Okay, so the 1 is going to be implied. Everybody's following that logic? So the 1 is implied. We're just going to put the negative sign indicating -1. Okay. And the negative sign is actually the dash or the whatever that is. Okay. Let's do one with a charge with with a number. Hydrogen phosphate. Once again, I don't remember. Hydrogen phosphate on this table is HPO4 2 minus. The bottom part of the table, hydrogen phosphate, HPO4 2 minus. Now the table has it as 2 minus. Sometimes, as you have seen me, I put -2, -2. Let's just do it with the 2 minus and see what it says. So HPO subscript 4, and then, oops, I need to do the superscript, right? 2, and then the dash, the minus.
Don't actually have to use the template to type it. You can just press the little like caret, like shift +6.
Oh, excellent.
It's just quicker to type. For some people, it might be a little bit harder.
Yeah, so let's
It'll
do.
automatically bring up the template.
Okay, let me try it then with sulfate.
Maybe in every class, you have the most knowledge about everything. So helpful.
Okay, SO4 is sulfate. Do you have a trick for the subscript?
There is one I saw it the other day, but I forgot it.
Yeah, it's
Shift
shift +6.
+6. But that's for superscript.
Yeah. Oh, for the subscript. Sorry.
For subscript.
The I thought
Not trick.
I'm directionally blind.
Right, no, that's okay. So is there a trick for subscript? I'm just going to go to a template.
I don't think so.
No, there was, but I did it by accident the other day, but I forgot what it was now.
Yeah, I used to know it too, but let's just, okay, so what is SO4 2 minus, I believe? So you said it was shift 6? Oh, great, that works. 2 minus, let's see. Oh yeah, it liked it. So that skips one click. Shift 6. I wonder what is the subscript.
Control equals for subscript.
Control equals is for subscript, perfect.
At least according to their shortcuts.
Okay, you know, there's people that work on the computer all the time tend to learn these shortcuts so that you reduce mouse clicks or trackpad clicks. I cannot hold that much information in my brain. I'd rather just follow, the clicking. But there's entire applications that allow you to have these shortcuts embedded into your computer. Now for dictating, I had to press the escape key twice, and I start dictating onto my computer. I don't know what is for yours, but for mine, it's escape twice. All right, questions about that? If not, let's just move on to the next one, which is the same, except that, different choices. So we're going to skip that one. Enter the formula for the polyatomic ion Na2CO3. So we need to identify the polyatomic ion ourselves. Sodium is not polyatomic, it's monoatomic. But CO3, the whole thing, is what we call polyatomic. So in that case, the identified ion is CO3. Now we need to also come up with the charge. For that, we can go back to the table, or we can simply put the formula here and work backwards. Okay? How do we work backwards? Well, we for sure know the charge of sodium is 1 plus. If this is 1 plus, that means that I have one of these, but there's a 2 here, which must have come from a crisscrossing. So the charge of the carbonate ion most likely is 2 minus. You can always confirm that, but if this gives you the right formula by crisscrossing, then you're 99.999% sure that that's correct. So express single charges as plus. Okay, so this is where we learn that we don't need to put the number for ones. I think it's the same thing, so I'm not going to write it. It's just CO3 with the charge of 2 negative. Okay, so now we are finally on the part of the chapter that talks about covalent compounds. I spent quite a bit of time on Tuesday talking to you about covalent compounds, how they are identifiable by simply looking at whether you have a metal or not. If you don't have a metal, if there's only non-metals, then it's covalent. If you have a single metal, then it's ionic. The lab today is super easy, you guys. I hate saying that. I don't like it when I make a comment like that because not everybody agrees with me. It may be difficult to some of you, but in my perception, it's not a very difficult lab, except that it does cover stuff that we haven't talked about. So we're going to spend some time today there, but I don't expect to use the 2.5 hours. Now, so in covalent compounds, you use these prefixes with some small rules that you had to remember. For instance, one rule that comes to mind right now is that when you have an oxide, and you have a prefix like penta that ends in that A, instead of writing pentaoxide, and this is just a quirk of chemistry, we are told that we need to get rid of the A and call it pentoxide. Oops. Okay, so there are minor rules like that. Another one is the mono. Mono is not used when the first element has only a single atom. So we're going to learn that by looking at some of these. I already answered this one, I guess, earlier. So sulfur dioxide would be, what was the question? I didn't even see it. On top, SO2. So if we had the hypothetical molecule SO3, then it would be sulfur trioxide. Okay? So we're just going to use these prefixes that are given to us. Okay. So let's move on. I'm sure they're going to be similar. All of these are called, by the way, binary because there's only 2 elements. So this one I also answered before, phosphorus trihydride. So phosphorus is only 1, so a P. Trihydride, the hydride ion is not an ion rather, but the hydride element as a covalent compound is H. And there's 3 of them, so PH3 would be the correct formula. I think it's a lot more straightforward than ionic compounds. There's a couple of weird ones. Let's take a look at this one, for instance. And let's make sure that we're still on covalent compounds. So nitrogen is a nonmetal, bromine is a nonmetal. Yes, this is definitely a covalent compound, a binary covalent compound. So what do they want? They want to name it. Well, we could be tempted to say mononitrogen, but it's only nitrogen. When the first element has only a single element, we do not use the prefix mono. If there were 2 nitrogens, then we would have to say dinitrogen. So nitrogen, 3 bromines, tri-bromide because we changed the ending to IDE. The first element remains the name that you see in the periodic table. So this Cl2 is not going to be chloride, as we have been calling it as an ion. Here is a covalent, it's sharing electrons. There's 2 of them, so it's going to be dichlorine oxide. Now, is it monoxide or oxide? What does it be correct? So let's enter it, because that will teach us another rule. So dichloride. And if I only put oxide, because there's more than one, let's see what it says. Incorrect, no feedback. So let's add the mono in front. Oh, and here we go again with the phonetic. Do I have to have 2 O's or only 1? Only 1 O. Just because it's still going to be sounding the same, I guess, and that's what I'm going to submit. Oh, what did it say? What is it not liking?
Dichlorine, right?
Ah! Chlorine. Okay. And I kept submitting the same thing. Dichlorine monoxide. I'm so sorry. Okay. Yes. Perfect. Okay. GE. Wow, you had to look that up. It's germanium. And I actually answered it before. So let's move on to question 23. Name each of the following molecular compounds. So molecular compounds and covalent compounds are the same thing. These are still binary, and we're still going to be doing the same thing that we did before. So it's a similar question. The last two questions, this is the same thing again. Use this passage, and I did read it before coming to class today. And it's, it's interesting because it gives you some information that some of you who work in an allied health field, perhaps in a hospital or in a clinic or in a doctor's office, you're going to recognize some of that stuff. So read it, but it's not necessary to answer the question. You could actually answer the question just by looking at this. The paragraph is just extra stuff. Okay. So that concludes chapter 6. And we move on now to a really interesting chapter. I'm going to turn off the, well, no, not yet. Now, before we start with this topic, I'm going to write the number that we use way at the beginning of the semester to sort of understand scientific notation. We had this number way at the beginning. In fact, I probably did write all of those zeros in front of you. This number has actually a name, and is named after the person who came up with the calculation to get it. And his last name was Avogadro, so we call it Avogadro's number. Now, is the chemistry dozen, if you will. A dozen, as you know, doesn't imply 12 of any particular items, right? It just means 12. So 1 dozen equals 12. Well, Avogadro's number is like a dozen, meaning you can have Avogadro's number of anything. You can have an Avogadro number of books, of students, of atoms, of molecules, of anything. It has a name, and a particular unit name, and I'm going to give you that in a minute. But before we do that, let's just talk about how big that number is. When I teach fully online, I used to have these discussions. So anybody has any idea what is the population of Earth today, or roughly? 8 billion. Okay, we're getting probably closer to 9 billion, but let's say 8 billion. Now, 8 billion in the US is written as this. 8, and then I believe 9 zeros. Not 12. That would be elsewhere, but that's 8 billion. How big is Avogadro's number? Well, imagine some ultra-rich, it doesn't exist, but if it existed, person giving 1 penny, 1 cent, to every person on Earth, but in fact an equivalent to an Avogadro's number. In other words, this rich person is going to distribute that amount of pennies among this number of people. How much money each person in the world will get? So how do we do that calculation? Do we divide this by that or that by that? Well, we divide this by that, right? So we're going to, let me open a calculator and just see if I can do that calculation, because it may not let me. Calculator. Let's see if we can do that. So 6.02 exponent 23rd divided by 8 1, 2, 3, 1, 2, 3, 1, 2, 3, equal. So every person on earth would get 7.5 times 10 to the 13 pennies. Let's divide that by 100 to see how many dollars every person will get. So divided by 100. Every person would get that much money if 1 penny of Avogadro's number were distributed equally among 8 billion people. That's how huge the number is. So that's 3 plus 3 plus 3, so that's 3 more, $7.5 trillion per person, 1 penny at a time, if you were to distribute that many pennies. So the number is humongous, but it's actually a real number. The name we're going to use to describe that number, because calling it Avogadro's number, I mean, it is what it is. That's what it is. But for chemistry, because this is equivalent to a dozen, what we're going to say is the following. That 1 mole, and that's the name that we are introducing today, as the name of the unit, of anything equals that many items. 1 mole equals that many items. You may once again wonder, 1 mole of what? 1 mole of anything. 1 mole of pennies, 1 mole of books, 1 mole of tables contains 6.02 times 10 to the 23rd tables, pennies, books, etc. We're going to use that number today, and we're going to go back to what we learned way back at the beginning of the semester and use conversion factors, dimensional analysis, to find some very interesting stuff, still using the periodic table, by the way. Okay, so brace yourselves. This is it. This is chapters 7 and 8 and 9, the culmination of preparation. We've been preparing for this moment all semester long. Now, if you look at the periodic table and you look, for instance, at hydrogen. So hydrogen has an atomic number of 1, but it also has a molar mass, an atomic mass. And in the periodic table is indicated as 1.00795. So the hydrogen molar mass equals to 1.00795. Let me make sure that I wrote the correct number of zeros, yes. Now that number comes straight from the periodic table. Well, we're going to put some units that we have used not before. We used to call them AMUs. We're going to give it a new value. We're going to call them grams per 1 mole, or grams per mole. To simplify, remember that the 1 is never written, so I just want you to realize that there's a 1 there. It's going to be just grams per mole. And as you can imagine, going forward, we're just going to say G per mole. Now that's a conversion factor, you guys. That's a conversion factor, as you may remember. That basically means that 1.00795 grams of hydrogen are equal to 1 mole of hydrogen. That equality comes from the molar mass. Hypothetically, if you could actually weigh hydrogen, because hydrogen is a gas, but imagine that it's a solid. If you wanted to weigh a mole of hydrogen, all you had to do is go to the lab, find a scale, and put 1.00795 grams of hydrogen, and that amount of hydrogen would have these many atoms of hydrogen, 6.02 times 10 to the 23rd, because that's 1 mole. We also have this as an equality, right? That's another equality that can be used for conversion factors. So there's going to be a lot of numbers here that we're going to have to deal with. But it's not that complicated. Now, what if I were to ask you a question? So let's start asking a question based on the information that we have on the board that is answerable. So how many hydrogen atoms are present in 5 moles? The plural of mole is moles of hydrogen. That's the question I want to address first and foremost before we go to other questions. So how many hydrogen atoms are present in 5 moles of hydrogen? Well, we have the equality that we need here to answer that question. We're going to do the same thing that we did way back a few weeks into the semester, and set it up as follows. So we're going to say, okay, we want to know the number of atoms, so we're going to put 5 moles of hydrogen multiplied by a conversion factor that eliminates moles and leaves me with atoms, right? That's what we did all the time, and that comes from the equality. Now, because this is like a dozen, I could actually say here 1 mole of hydrogen atoms equals 6.0 times 10 to the 23rd hydrogen atoms, units. I just added that. You're going to have to add it every time that you use this equality. So that equality I'm going to use as a conversion factor, but I need to put moles on the bottom so that they cancel each other out. I need to put atoms on the top so that they remain. So from that, I'm going to put this number first, times 6.02 times 10 to the 23rd atoms of hydrogen, divided by, because this is a conversion factor that is coming from this equality, review your stuff from earlier if you don't remember, 1 mole of hydrogen atoms. So 1 mole So moles of hydrogen and moles of hydrogen cancel each other out. And we're left with just atoms. Then simply multiply those two numbers and report your answer. So 5 times 6 is 30.02 times 10 to the 23rd. That's not scientific notation, though. I need to move the decimal point 1 place. We're just doing what we did before. So now it's 3.002 times 10 to the 24th, because I have to increase that number by 1 since I moved it 1 decimal point. If you don't know what I'm doing, you need to review your scientific notation knowledge, because this is stuff that we already learned way at the beginning of the semester. And now we just put the units, atoms of hydrogen. And that's our answer to that very first question. How many grams of hydrogen are in 5 moles of hydrogen? So that's the second question I want to address. This number, the molar mass from the periodic table, so we have this equality, right? This tells me that 1 mole of hydrogen is equal to 1.00795 grams of hydrogen. So what happens next? Let's set it up. We have the information that we have is 5 moles. I need to multiply that amount by a conversion factor coming from the molar mass, coming from here. Now that conversion factor has to have the units of grams on the top because that's what I want as my answer. It has to have the units of moles on the bottom so that they cancel each other out, right? So from this equality, which one would place the grams on the top? The one in which I write 1.00795 grams of hydrogen are equal to 1 mole of hydrogen. Okay? So if we carry out that operation, what happens to moles of hydrogen? They cancel each other out. And we are left with the answer, which is how many grams of hydrogen are present in 5 moles of hydrogen. I'm not going to do the math, but whatever that comes up to be, that would be the answer. So here's what I propose, because perhaps you're not completely comfortable with these equalities, and then using those equalities as conversion factors. So let's set up, and I keep calling it that, but that's what it is, a cheat sheet, you know, a guide, if you will, to sort of answer multiple types of questions with this one guide. So may I erase these?
Yes.
Okay. In this chapter, we're going to be making conversions quite often between moles, items. Most of the time, the items are going to be either molecules or atoms, and then grams. So we're going to be moving from items. Let's call these, for the most part, they're going to be atoms or molecules. I mean, I'm not going to be asking you for books or eggs or tables. We're going to be asking for chemical things, atoms or molecules. So we're going to be moving from atoms back and forth to moles. The unit being mole. And then we're going to be moving also from moles to mass, in particular grams. So we're going to put grams here instead of kilograms or ounces. It's going to be grams most of the time, back and forth. Okay? That's essentially what we're going to be doing. In the example that I asked you first, we actually move from here to here. And then in the second example that I gave you, we move from here to here, to grams. So is there any way of remembering this without having to go back to the equalities? Well, we're going to put Avogadro's number here. Avogadro's number can be abbreviated as Na. So that is 6.02 times 10 to the 23rd. Now, if we have items and we want to obtain moles, according to that equality, what we would have to do is divide by that number. So to go from items to moles, we divide by Avogadro's number. If we want to move from moles, let's say we have 2 moles of sodium, and we want to know how many atoms of sodium are in those 2 moles, we're going to multiply times by Avogadro's number. So multiply divide. To me, this is not the best way, but to some of you it is. To some of you may not be. The equalities may be. You choose whatever works for you. Now, let's take a look at what happens when we have moles and we want grams, or when we have grams and we need moles. We're gonna need the molar mass. The stuff that we get from the periodic table, or later today, from a calculation that we're gonna make. So, if we wanna go from moles to grams, so we have moles and we want grams, the molar mass gives you grams per mole, right? So if we multiply these by grams per mole, that cancels moles out. So to go from moles to grams, we're going to multiply by the molar mass. If we have 10 moles, and we want to know how many grams of hydrogen are there, we multiply by 1.00795 grams in 1 mole. That cancels moles out, it gives me grams. So we multiply by the molar mass. But if we want to work in reverse, if we have grams of a substance and we want to know how many moles are in those many grams, we're going to divide by molar mass. Really dividing by molar mass means flipping this number. Okay? Now we have grams times the reverse of that, 1 mole over 1.00795 grams. That cancels grams, leaves me moles. That's what I want to do. I'm really dividing by the molar mass. You take your pick. If you want to use equalities, I think it's a sure thing. If you want to have this diagram in front of you on a piece of paper when you're doing a problem, by all means do that. Whatever works for you to get to the right answer. They are both following the same logic. Turning equalities into conversion factors. Now, here is a question for you. What happens, what do you have to do if you have a problem in which you are given the number of atoms, you're given this, and the problem wants you to report how many grams that many atoms weighs? You want this. There's no shortcut. You had to go from here to here first, and then from here to there second. I mean, it's like if you want to go from Fall River to Boston, traveling on 24. Well, you had to go through, what is it, Bridgewater? Whatever town is between here and Boston, you cannot avoid it. I mean, you can, but in my analogy, you had to go through that place. So to go from here to here, we have to go through moles. To go from grams to atoms or molecules, we have to go through moles. So there's 2 calculations that you have to do. Just take a deep breath and do one calculation first. Take a second deep breath, do the second calculation second, and you'll be okay. Now we're going to be doing many problems, but there's one more thing that we need to talk about before we start even considering problems, and that is the following. So far, we look at the periodic table for molar masses of elements. But can we look at the periodic table for molar masses of compounds? I mean, I said earlier, you really cannot weigh hydrogen in the lab. But you certainly can weigh sucrose. Anybody knows what sucrose is? It's table sugar, right. So this is cane sugar. Now, table sugar, or sucrose, has a chemical formula that is a little bit more complicated than some of the ones that we have looked at. But it's not a big deal. We're just going to write it here. C12, H24, O12. I'm going to confirm that because there may be one less oxygen there. I just don't want to mislead you. C12H20, yeah, so there's one water molecule less. H22O11. I should have done glucose. That one is exactly half of this without removing water. But we have sucrose in front of us, no big deal. C12H22O11. What is this telling you? Well, the same thing that we were finding out about all of those formulas that we looked at before, K3PO4. Well, K3PO4 means that there's 3 Ks, 1 P, 4 O's. Here, this formula tells me that 1 unit of sucrose has 12 carbons. Now, when I say carbons, I mean atoms of carbon. It has 22 hydrogens. That's what the formula tells me. And it has 11 oxygens. And actually, if we want to be speaking chemical jargon, I wouldn't say 12 carbon atoms. I would say 12 moles of carbon, 22 moles of hydrogen, and 11 moles of oxygen. That's a little bit more. That wasn't a drill or anything, was it?
No, it's my phone.
Mine did it at exactly the same time as yours. So that's why I wonder if it was some sort of a drill. There was one on Monday if you were on campus. So anyway, so 1 mole of sucrose, 1 unit of this has 12 moles of carbon, 22 mole of hydrogen, 11 mole of oxygen. That's chemical jargon. Now, the periodic table helps you with molar masses, but it doesn't do it for you when you have a formula like this. So my question right now for you is, what is the molar mass of sucrose? I mean, we know that the molar mass of hydrogen is 1.0079. We look at the periodic table. We know that the molar mass of oxygen is 15.9994, according to the periodic table. We know that the molar mass of carbon, according to the periodic table, is 12.011. But what's the molar mass of sucrose? Well, let's do the calculation. Now, I'm going to take a picture of that before I erase it. I hate having to think about it more than once. So I'm going to erase that, but I'm going to, just for people who are not here, take a picture of that. There we go. Just to share the same thing. How do we calculate the molar mass of sucrose? I mean, of course, you guys, you can ask Google, right? I mean, you can go to Google and say, give me the molar mass of sucrose, and it will in one fraction of a second. But you need to know where that number comes from, at least once in your lives. It comes from adding the molar masses of each of these ingredients, one at a time. So we're going to say, okay, molar mass of sucrose there are 12 mole of carbon in 1 mole of sucrose, right? That's what that 12 tells me. I'm introducing this new topic, this new concept as I go. I'm telling you right now that a formula tells you the number of moles of each element in that 1 unit. So 1 unit of sucrose has 12 units of carbon. 1 mole of sucrose, 12 moles of carbon. But I need to multiply that by the molar mass of carbon if I want the molar mass of the total. So the molar mass of carbon, according to the periodic table, is 12.011. So 12.011 grams per mole. I told you we were going to simplify it. And then we're going to put equal. We're going to do the same for the hydrogen. So we have 22 mole of hydrogen times the molar mass of hydrogen. And then we have 11 mole of oxygen times the molar mass of oxygen, which according to this periodic table, sometimes we just round it off to 16, but I'm going to put the number that is there. 15.39? Yeah, 999 and then 4. Okay, so if we carry out that operation, and I know that I have the screen off, but I think I still have the calculator here. No, I don't. If you can do this calculation on your own, that'll be great. I have 12 times 12.011. I get 144.132. Then I am going to multiply 22 times 1.0079, 1.00795. And I get 22.1749. And then finally, the oxygen is 11 oxygens times 15.9994. And I get 175.9934. 175.9934. If I add all of those together, I'm going to get the molar mass of sucrose. So plus 22.1749. And be very careful entering your numbers so that you don't make a mistake by simply putting the wrong digit, as I may have done. So I'm going to share with you now the screen. So I get 342.3003. Now, I'm not worried about significant digits at this point, because what I want you to understand is how you calculate a molar mass, not whether or not this number of significant digits is correct. Now, I'm going to keep the units of grams per mole, although I was here canceling out moles, because this is my molar mass of sucrose. And yes, it is that time consuming. So here, when I looked up the formula for sucrose, I thought I had seen the molar mass. The molar mass is sometimes called formula weight. Same thing. That's a synonym. So let's take a look. I don't know. I'm going to click on any of these links and see if they give us the molar mass. Oh, there it is. Monoisotopic is tiny, tiny, tiny. I just want to see if we're in the ballpark figure. 342.29, 342.30. Almost the same. Okay? If I take these to only 4 significant digits, that's 342.3. 342.3. So we got spot on. Now, obviously, you don't want to have to be doing this all the time. We used Wolfram alpha before. And you're welcome to use Wolfram alpha anytime that you're doing chemistry. This is AI for science. Molar mass of sucrose. Of course, you can use the Wikipedia, but this is intended for the sciences. And the molar mass of sucrose, 342.3 grams per mole. Now, this is a lot of information in very little time, but it's not unmanageable. If you spend the time looking at the homework problems, I know Kelsey already finished chapters. I guess you finished chapter 8 too. I mean, from what you just said.
That's why I was doing
Chapter 9. Okay, so, but it's manageable, right, Kelsey? I mean,
but chapter 9 is, I think chapter 9 is harder.
Definitely, I agree with you. Because we're going to be talking about percent yield. We're going to be talking about limiting reagents. So there's a number of really kind of challenging concepts, but not terribly challenging, trust me. Now, we're not done with what I wanted to introduce you on this idea of chapter 7, the so-called Avogadro number and molar masses. We need to talk about something called percent mass composition. And I'm going to leave sucrose as the example because I think it's doable. Before we do that, let's do a quick calculation. So can you answer the following question? What is the molar mass of water? And this is regular water, not heavy water, because there's other waters. This is just regular water. I'll give you a couple of minutes, and 2 significant digits would be great. You can give me 3 significant digits, but what is the molar mass of water? Oops, it's there, so I better not. Oh my God, I'm out of time. So very quickly. Formula of water, H2O, right? So that means there are 2 hydrogens, 1 oxygen. The 2 hydrogens need to be multiplied by 1.00795. The 1 oxygen has to be multiplied by 15.9994 grams per mole on both cases. This is not 10, but 1 oxygen. Oxygen. So you should come up with about what? Did you do it? Oops. I'll put it here for you to see. Ready? So you should come up with 18.01 or 0.02 grams per mole. 2 times 1 is about 2, 1 times 16 is about 16, 16 plus 2, 18. Yeah, it's about 18. Okay, so I don't want to rush. We'll talk about percent mass composition next week, and then we'll be ready to do some problems. Okay, so I'll see you in lab in about 15 minutes.